Hello everyone, I'm Nirali Vasoya and I'm part of Core Function Pack team with NSO. Today I'll be talking about NSO performance and scale for reference use cases NFVO and T-SDN with NSO 6.0. So let's get started. Our main objective is to see the capabilities of NSO for scale and performance for two use cases. One is NFVO core function pack and the other is T-SDN core function pack. NFVO core function pack is more of a virtualization based use case where we spin up VNFs, and it is more of a RFM based service at NSO level. So there are lots and lots of redeploys to converge the service. For T-SDN core function pack, it is more of a physical device configuration use case. So you have a large or huge network topology of physical devices and you're trying to configure services on those. Our aim is to understand a few things. One is how NSO scales and performs for different use cases and what can be expected in terms of resource requirements for each use case, and how different deployment options can help achieve different scale and performance targets. Okay. We'll jump into NFVO first. NFVO core function pack is essentially NFV orchestration function pack. It's Cisco's version of HC Manostack for NFVO component. It has two main functions. One is instantiating and managing lifecycle of VNFs on Vim via a Sol3 or a generic VNFM, as well as Cisco ESC VNFM. And the other function is to allocate resources on a Vim, whether it's OpenStack, VMware, AWS, or any kind of VIMs for a given VNF. Our focus today is going to be on instantiating and managing the lifecycle of VNF and see how NSO scales for this particular use case. Before we jump into any kind of numbers, let's look at how the NFVO service flow looks. This would help us understand how the internals of the service work and how and where NSO would scale. Right? So, as you can see in the diagram, there are four main components here that will be interacting with each other. One is NFVO, which is a core function pack, a package on top of NSO. Another one is VNFM, which is a Sol3 VNFM, a generic VNFM, and then Vim, and then VNF. So the request comes to NSO where to create the service. So you create your VNF service request. NSO or NFVO goes to VNFM to create the resource ID and then sends an instantiate action to say VNFM that the VNF is ready to get instantiated. Okay, and then we see a lot of events coming in from VNFM to NFVO, and these are the events that would trigger redeploys on NFVO service to be able to reflect the state of ongoing VNF creation. So it starts with a starting event and then a grant request to NFVO, which is then responded by NFVO, wherein VNFM goes and requests the Vim to deploy the VNF. And then once the VNF starts getting deployed, you will see a processing event. And then there's the check alive state, wherein VNFM checks if the VNF is alive to mark it completed. And then eventually the last event is VNF complete event, which redeploys the service and converges the service on NFVO. This is the infrastructure and methodology that we use for NFVO scale test. There are a few main components here, starting with automation framework. Automation framework works as a twofold unit here. One is to, as a OSS or VSS, sending create request to NSO, and as well as monitoring resources on NSO. And then you have NFVO core function pack, which is installed as a package on NSO. And then you have Sol3 VNFM, which is the ESC version of Sol3 VNFM. In terms of infrastructure, we are testing with NSO version 6.0, NFVO 4.7.2, which is the latest version of NFVO, with the standard system configuration for scale. And the methodology is to create 10K services in one single service in a commit. and commits are happening back to back without any sleep. So you commit one service, and then the next service is committed as soon as the commit from the first service is back. And the VNFM that we're using here is a netsim or a mock version of the actual VNFM. This is to isolate any infrastructure dependencies for this particular scale test. And the netsim or the mock is configured to send VNF instantiate notification every 5 minutes. So when it gets a create request, it sends a starting and a processing event, and then waits for 5 minutes before sending the instantiate complete notification. This is to mimic the time a real VNF would take on a real setup, right, to bring up. So with this method and infrastructure, these are the numbers that we see with NSO 6.0. So, and these are the numbers that we're going to compare with what we had seen with NSO 5.4 previously. So the number of VNFs or the number of services that we create here is 10K. The number of threads that push the service commits is going to be two different methods. One is single thread and the other one is 5 threads. And this is no LSA, no commit queue, and no HA setup. Now, as you can see here, the total time to converge the services has significantly reduced with NSO 6.0 with 5 threads. It is almost a 3 times improvement over what was seen with NSO 5.4. Also, you can see the average commit time here. So with NSO 5.4, the average commit time was 2.8. With single thread, it was around 2 seconds. But with 6.0, with 5 threads, the time goes up to 10 seconds. And this is because there's a lot of services getting created in parallel, but NSO is busy and has to do conflict resolution checks now with the new concurrency model. Also, you can see that there's not much difference between convergence time of single thread versus 5 thread. It's almost similar, and that is because this particular service, NFVO service, relies highly on redeploys of a service, and redeploys are by themselves parallelized with NSO 6.0. So that's why there's not much difference in this particular case between single thread and 5 thread. Now, and the resource utilization is pretty standard. If you look at the CDB footprint, it's quite reduced. These are some of the other improvements in NSO 6.0 that leads to this better CDB footprint. Okay, so this is NFVO use case. Now, let's look at T-SDN core function pack, which is the PNF orchestration, a physical network function orchestration. This core function pack is an automation solution for transport SDN. It essentially has few automation functions, which is one is to configure segment routing policies like SRODN and SRTE on physical devices or the XR routers. And the other one is configuring L2 or L3 VPN configuration. For this particular test, we are going to focus on segment routing configurations or the policy configurations on the XR router. Again, let's look at the service flow and how it looks. There are two main components here, T-SDN and XR 9K. In terms of the flow, you get a create request from northbound to create the service policy. T-SDN function pack then decides what type of device needs to be configured. It picks the device configuration template and starts applying the device configuration onto NSO device tree. There are two options in this case. One is you use commit queues to configure the devices, or you do not use commit queues. It's a synchronous commit, right? So for our test, we are going to focus on the commit queue part where you have multiple devices getting configured in parallel, and this is happening asynchronously. And once the devices are configured, there's a redeploy on the service, which converges as a plan. Okay. This is how the infrastructure and the methodology looks for T-SDN. It is using the same automation framework to push the services and monitor the resources on NSO. This time, T-SDN core function pack is the package deployed on NSO, and and there are a bunch of ASR 9K or XRB 9K devices that are deployed or that are being configured. In terms of infrastructure, again, we are testing with NSO 6.0, latest release of T-SDN, which is 4.0, and standard system configurations for scale environment. In terms of methodology, again, we are trying to create 10K services getting committed one after the other in single service per commit. There's no sleep between the commits. So as soon as the first commit returns, the next service is committed. The important thing here is there are in total, there are 300 NetSync XR CLI NetSync devices that are distributed across these 10K services. And per service, it uses 4 total devices, right? So for the first service, you use the first 4 and then the next 4. And then once you run through 75 services using all 300 devices, you again start over with the first set of 4 devices. Okay. Now, in terms of numbers or the test results, this is how it looks. So we start with 10K services. Each service has 4 devices, total of 300 devices. We'll also test this use case with single thread as well as multi-thread. And we will test with commit queue enabled for this particular case. There's no LSA or HA in this case. Now, again, we're going to compare this with the numbers that we see with NSO 5.4. If you look at the total time to converge, the improvement is about 2.5 times for this particular use case. The average commit time is, again, higher for multi-thread case. It's better for the single thread as expected. And comparing single thread versus 5 thread, there's an improvement of 1.5 times. And this is because here we are not dependent on a lot of redeploys to converge the service. There is 1 redeploy per service for convergence. In terms of memory and other resources, it's pretty standard. Again, the CDB footprint is little lower than what we saw with NSO 5.4. So these are the 2 use cases that we have tested for NSO 6.0 and have seen quite a bit of improvement in terms of scale as well as performance. Let's look at what are the recommendations and summary from this test that can be followed by users to achieve the scale and performance for their use cases. So up top, the first thing is, as we can see, the numbers were quite different between NFVO and T-SDN. So the numbers for scale and performance could vary based on what use case you are trying with or what is the environment that you are trying with. And for that reason, it's highly recommended that the tests are done to determine what kind of scale and performance numbers you would see for your use case. Okay. And it is also advised to test bulk operations, try to do thousands of creates and deletes and updates. And this should be planned so that you could know up top what will be the resource requirements as well as what scale and performance can be expected from the use case. The other main thing is not to mix this bulk operations with any other changes that are being done in the system, right? So it's good to avoid any kind of other operations while this bulk creates or deletes or updates are happening. Now, in terms of planning to start consuming 6.0 with very minimal changes for significant performance gains, these are the few things that are recommended. One is you have to make sure the service code is thread safe, because now the services would run in parallel and it requires the thread safety to be present. The other one is using multiprocessing call points for Python packages. Multiprocessing is important for when you have multiple call points in a Python package, right, or in a Python service, or in your action points. For things to run in parallel, it's essential that we change the call point model to multiprocessing. The other one is to make sure the service code is idempotent, because due to conflicts, your service callbacks could rerun. So you have to make sure that they are idempotent and that don't create any other side effects. And as we saw with the results, we would expect to have more CPUs and more RAM if you are doing more operations in parallel. And you could see more CPU cores being utilized by NSO with 6.0. And the last one is expecting higher commit response times if you are doing multiple things in parallel. Things would get faster, but the commit response time would increase compared to if you do the same things in a single thread. Okay. In terms of summary, we can see that NSO scales and performs well for virtualization and physical device configuration use cases. In terms of total service convergence time, we can see thousands of services could be created in few hours. So NSO scales very well for these two use cases. We can see compared to NSO 5.4, there is 2 to 3 times improvements with NSO 6.0 with very minimal changes in the function packs or the services. And about 20 to 30 services are converged per minute, which is a good amount of parallelization. And significant performance improvements can be seen when we do a multi-thread kind of a scenario, specifically in cases like T-SDN, where you have 5 threads creating services in parallel with 4 devices each. In terms of resource utilization, the numbers show that it was quite a linear growth, and optimally resources were optimally utilized. Okay. And there are more improvements that are going on, and with future versions, there will be more improvements to this number that we see today, but this is just a start with NSO 6.0. And that brings me to the end of my presentation. I would like to thank you for your time and attention today. If you have any questions, feel free to reach out through usual channels. Thank you.